Hello and welcome to this new tutorial, and mostly welcome to our ultimate evolution strategy. I'm talking of course about Covariance Matrix Adaptation Evolution Strategy, also called CMAES, and which is the evolution strategy we'll use for our controller, to find its optimal parameters. So, first thing first, I've already mentioned it, but let's remind the very important particularity of that evolution strategy. It is that this time the standard deviation, when you're sampling the points around the mean, is no longer fixed. That was the case in our first evolution strategy, the simple evolution strategy. Remember that the standard deviation sigma was fixed, and that's why that the blue points surrounding the green point are always in the same range. Well, that's the sampled points always in the same circle around the mean. Well, that's because the standard deviation was fixed. But now, the particularity of the CMAES evolution strategy is that it is no longer fixed. The standard deviation noise parameter is no longer fixed, and that's why that now you see some blue points surrounding the mean within different ranges. And that's a much better solution because indeed, if you have different mountain shapes, like, not necessarily higher and higher, well, you might get stuck in a local optima. You might not be able to reach the global maximum if indeed the standard deviation is fixed. But now, because the standard deviation is varying over time, over the iterations, well, when the standard deviation is large enough, well, you will be able to go over a higher mountain in that series of mountain shapes to therefore be able to catch that global maximum. So it is by far one of the best evolution strategies with, the other one, which is the PEPG. We'll come to that later. Remember that CMAES is used for a reasonable amount of parameters, meaning less than 1000. But when you have thousands of parameters to optimize, you will rather use PEPG. But in our case, the full world model, where, the controller is simply a single layer linear model, well, we definitely don't have thousands of parameters, and therefore the CMAES is clearly the best evolution strategy to use for that particular case. Alright, and now let's get into the math. So you understand the principle, the main principle of the CMAES. It is going to be about varying the standard deviation. So let's see how it is going to do that. Alright, so first of all, well, let's have a quick refresher of statistics, and especially about covariance matrix. You can guess by the name of that evolution strategy that a covariance matrix will come into play. So before we get to the math definition of a covariance matrix, well, you need to understand this. So this is simply the mean of the x coordinates of all your samples. So n is the total number of samples at each iteration. Same for mu y, which is the mean of the y coordinates in that same set of samples. Then once you have mu x and mu y, well, you're able to compute indeed the variance of x, the x coordinate, and the variance of y, the y coordinate, with these respective formula, which is just the mean of the squared differences between the x coordinates of the samples minus the mean of the x coordinates in the whole set of samples, and same for the variance of y, which is the mean of the squared differences between the y coordinates and the mean of the y coordinates in that same set of sample. And then once you have this, well, you can compute what we call the covariance between x and y. Not yet the covariance matrix, we'll get to that, but the covariance between the x coordinates and the y coordinates in the whole set of samples, which is, as you can see, the mean of the product of the differences between the x coordinates and the mean of the x coordinates, and the differences between the y coordinates and the mean of the y coordinates. And so as soon as you have these three factors, well, you are able to get directly the covariance matrix, because indeed it is going to be, a matrix of 2 by 2 elements, meaning with 2 rows and 2 columns. The first element at the upper left of the matrix will be that sigma x squared. Then the element at the lower right of that matrix will be sigma y squared, and then the other two elements will be the same, sigma xy. So that's the covariance matrix. But then the covariance matrix, as it is right here, will not be useful for the evolution strategy because indeed that's an estimate of the actual covariance matrix that we originally sampled from, and what we want to do instead is to have another covariance matrix which will allow us to sample the next generation of parameter solution. And so that's where CMAES comes into play, because it will modify the classic computation of the covariance matrix by first only keeping the 25% best solutions from the current set of sampled solutions. Then from these 25 best percent, it is going to compute first the mean of the x coordinates, so exactly as it was the case here, but only for the 25% best solutions. Then same for the mean of the y coordinates, still among these 25% best solutions. So it doesn't have to be always 25%, this is just a common choice here, but it could be 20%. So you compute the mean first, and then that's where the second important change will come into play. Here, when you're computing the coefficients of the covariance matrix, well, instead of, subtracting here by the mean of the x coordinates of the new generation, g plus 1, as it is the common formula of the covariance matrix, well, you're going to subtract by the mean of the x coordinates of the current generation. So you're not going to use this, which you've just computed, but exactly this previous mean of the x coordinates we computed before in the original set of parameter solution, before we extracted the best 25%. And then same for this second factor. Instead of computing as it would be the real computation of that covariance coefficient, well, you're not going to take the mean of the y coordinates of that new best generation. You're going to take the old one, meaning this one, and then same here for the last two parameters in the second diagonal of the covariance matrix. Well, instead of subtracting here by the mean of the x coordinates of the next generation, you're going to take the current generation, and same here, instead of taking the mean of the y coordinates of the next generation, you're going to take the current generation. So that's the little hack here, which is done in two steps. First, taking the 25% best solutions, and second, replacing in these means, well, the next generation by the current generation. And so then, once you do this, well, you have that hacked covariance matrix, and with that hacked covariance matrix, well, you're going to sample the next generation of candidate solutions. And so here we can see the different steps. Step 1, we calculate the fitness score of each candidate solution in generation G, before we extracted the 25% best. So we just look at basically the value of the function f of x and y for each of the blue points, meaning for each of the sampled solutions. Then step 2, we isolate the best 25% of the population in the current generation G. In purple, I'm not sure if you can see it well. I'm a bit colorblind, so I'm not sure if the author highlighted that well or if this is the same, but we clearly understand what this means, right? We just isolate the 25 best solutions which have the 25 highest values of f of x and y, still in that original generation G. Then step 3, well, we only keep those 25% best solutions and we remove the other one. However, we keep the old mean, that mean of the x coordinates we had for all these sampled blue points here, and same, we keep the mean of the y coordinates of all these sampled blue points here. And that's because, we keep the old means in the computation of the covariance matrix for the new generation. All right, and then as we can see, well, with the new extracted 25 best samples and these old means, we calculate the covariance matrix of the next generation, and using now again that new covariance matrix, we're going to sample your new set of candidate solutions using the updated mean mu of the next generation that you computed in step 3, and of course the covariance matrix C of the next generation, which same you computed in step 3. So in conclusion, that's pretty similar to the simple evolution strategy, except that we use this hack to vary the standard deviation sigma, which will therefore allow us to get indeed these different ranges of the sampled blue point surrounding the mean, meaning the green point, and catch that global maximum regardless of the complexities of the mountain shapes. And now, what's really important to understand, you might be wondering how that hack on the covariance matrix allowed us to overcome that local optima problem, to be stuck in local optima in case there are complex mountain shapes. Well, it is clearly stated here. The fact that CMAES can adapt both its mean and covariance matrix as we've just seen, well, it can decide to cast a wider net. That's when the variance is large, the standard deviation is large, as we can see here, or here right now. Right now it's really large. Well, it can decide to cast a wider net when the best solutions are far away. When the best solutions are a couple more mountain shapes further. So, and on the other hand, it can narrow the search space when the best solutions are close by, when they can be in the next mountain shape. So that's a pretty fascinating hack, in my opinion. It's really good that we can see this amazing simulation here. It really helps understanding better the intuition. And now, well, let's jump into the code so that you can clearly see where it is. Well, you won't miss it. It was called by the author CMAES within a class. However, this time you don't have the from scratch implementation, because indeed we import the CMAES evolution strategy, in that self.es object variable of the CMAES class, but it is created as an object of that built-in class CMA evolution strategy, which we import from that CMA package that we'll install later on. So you don't have the implementation from scratch. However, you still have the common process among the evolution strategies, with the ask method, the tell method, the method that returns the current parameters and best parameters from the set of sampled solutions. But indeed, if you want to have all the details of how was built this CMAES evolution strategy, well, you will need to find the open source code of that class, which you can do. But I think at this point, the most important for you is that you get the intuition of how CMAES works. And the strong principle is that we make that standard deviation vary depending on how far we are from the best solutions. And the second important element you need to know, and which I'm going to remind one more time, is that you should use CMAES when you don't have too many parameters to handle. And by too many parameters, I mean thousands of parameters. And that leads us to the next evolution strategies, because indeed, when you have thousands of parameters to optimize, well, you will rather use the PEPG evolution strategy or the OpenAI evolution strategy, because indeed you will see that these are powerful evolution strategies that use actually different tricks to handle a large amount of parameters. And we'll see exactly what these tricks are in the next tutorial. Until then, enjoy AI.